Get the pins, right pins. Yeah. Cover it here.
Okay, folks, I think we're nearly ready to get going again now. Okay, thanks everyone. It's good to see some of you are still here. Obviously the others were just here for the free lunch. Glad you could stick around. We've got two more presentations this afternoon. So first up we've got Gustavo Batista. He's going to talk about numerical model calibration using probabilistic approaches. So I'll hand you over to Gus. Thanks, Gus.
Hi everyone, thanks for the opportunity. I'm being here. My short name is Gus. I have some experience at mining in Brazil. In late the last year, I moved to Perth when I studied General English. So my English is still not very good. Let me know if you don't understand me. I can try again. My presentation is about the numerical model calibration. Use probabilistic approach at structural control or Dilution case in sublevel stop method. This is my master degrees when I presented last year in Brazil. This is about the Serra Grande mine when I worked more than 5 years. The company AngloGold Ashanti. One of the reasons for start my master was to understand the cause of overbreak involved in a mining project. So, why does this happen? Is it possible to pre-empt this? How would one approach the problem? What would be the desired outcomes? What is the best layout for this mine? Well, what I was looking for at the finish my master degrees, I look for quick and efficient tools for the back analysis, confidence in design, accuracy estimation of overweight, mine impact of the mine, quant risk in terms of money. This paper is the main published. I use it to construct my master, and I give mentor about the geotechnical team, Emmerich guys. Kubus give me a lot of support to do this. And this was the mine project for the 750 meters depth. It is a sublevel, top-down, narrow vein, without rock fill. Mine in yellow, the stop planet, and the ore drive is in gray. This was the result of the mine where I see the addition of the mine with the plane of the form colors. In green is a good addition, okay, good addition. In yellow, overbreak of 1 to 2 meters. In red, 2 to 3 meters, and in the dark red, more than 3 meters. In the addition, it's possible to observe the extension, one extension. This is caused by a structure present in the rock. So let's look at the which structure conducts in the stability. In here, the all structure or persistent joint data. This is a joint family. This case of instability in the foliation I use to the calibration the ubiquitous joint. In the main structure, I can do the generate the max structure from the persistent structures. The main steps and the when the calibration, the model in Map 3D are the model, this is my model, the model showed as representative was possible with the planet, the sequence, the first, second, and finally in here, showed the same at the mining. The grid, my grid is in here, must include the region of the analysis, and the mass of the grid showed is small enough to have a good resolution. The data analysis from normal and shear stress should be on the surface failure in here, in the green. Only these points. Okay. To understand the possibility of failure, I analyze the shear stress and the normal stress for the 2 overbreak mines. In the first, in here, with the 90% reliability, it was possible to determine the cohesion from 3.3 MPa and the friction angle 23 degrees. And the second, with 86% reliability, was cohesion at 3 MPa and the friction angle 25. So I run the map 3D again with the new data and check if the result would be compatible with the failure. Now, this is the results in yellow in here. Are values of excess shear stress, so unstable. In green are values below shear stress, so stable. The purple line is the result of the mining, and the model is very similar to the minage. To understand the failure, I analyze 557 datas, cohesion datas, bisect the dispersion of these data and fix the friction angle. So I return to map 3D, I insert the cohesion of 10%. This is 10% example. I go to the number 2.3 and I use the 90%. I use the cohesion 3.5. Cool. And check the new results. This is the failure surface in the blue, I can have one failure in 10 events, the probability 10%. This is a conservative model. And in here, in the hedge, the line hedge, is the failure surface that can occur 9 in 10 events. This is an optimistic model. Now, I understand the magnitude of the failure and its probability of the one event occur. So, it's normally every day at the mine, and you ask, how are you? Which model will you choose? Where you put the cables, bolts, to keep the mine stable? How much risk will you accept in your project? And how important is safe mining in your company? This zone is my uncertainty. It is caused by the heterogeneity, the rock mass, model uncertainty inputs in the model, and not least by the operation quality. Every day we have to choose one. This is your job. I can choose one this, and don't understand, or you understand the magnitude, the failure, you share the staffs and choose the best position. Not better for me, geotechnical, or better for engineer mine. It's better the company. Now the company, because for me, I use the 4.6 meter. In the mine engineer, use 2.2. So, in the last result of my master's degree, I was to propose a new layout for the mines from 800 meters to 1,000 meters in depth. Now, understand the structures that conduct stability, calibrate model, make the prediction of stability. Second, in this old layout, my rib pillars help me little because my main structure in this position. So this was replaced by steel pillars in here, and steel pillars, with the large openings in the strike and which out connect to the deep. The results were much better. The dilution used the more than 50%, now less than 20%. And some tests in the new layout was done. The first, a more conservative steel pillar in here. In second, I recover part of the steel pillar. In here, there was underbreak in the close of the mine. And finally, the lastly, one ideal steel pillar for the company. Now I put risk in my model. In here is a move, so the integration of geotechnical data with the mine adherence. In yellow, my mine plane, in green, my ore drive. Now you can see the adhesion of the mine planage. You can see the adhesion. I can put my domain classification. In the blue is good and the red is bad in Q system. Now you see the structure, the persistent structure. I have a big structure. In here is one. In here I have other. So I can construct the macro structure, my mine, and I understand the quality, the rock structure, the build, do the instability. This new layout was the severe other positive points. Example, this is more faster, then I save money. I need open less than start the sublevel, so I save my money. My hard drive is more distance than other, so I save my money. This is more less than overbreak, so I send my money. I want to share with who can do this in practice. This example on the Map3D website is the address in here. I made some modifications to the example to make it more operation. In blue is my layout, my plane model, and in red is my overbreak. So this is my grid. I can do the analysis, the calibrate my model. So I use the shear stress and normal stress to obtain the friction angle and the equation. This is my always grid. I can do analysis. Now you see the sigma 1, and this is a sigma 3. So I can get the shear stress and normal stress only the surface, the failure. So I construct the line. I get the points. I can do this again. So after that, I put this in the graphic in Excel, and I understand my cohesion and my friction angle. Use the shear stress and normal stress. It's a good correlation. So when my calibrate the cohesion and the friction angle, I use the main structure, the instability, that mine. When I return in Map3D, I can put now cohesion and friction angle, the calibration, and the structure condition, the stability. This is the results. More than 0 is excess shear stress, so unstable. Less than 0 is stable. In the black line, where is my surface failure, and my model in yellow. This other example, now example is Smart Mine. They use data available with the Gen4G software integration in the Map3D. Now it's the same example. I get the coordinates and the shear stress, normal stress. Now I get always information. I put the Excel, I save in the CSV, I open the Gen4G. Now you can see the stock planet is the same, the other example. It's my overbreak. You see my grids, a lot of grids, a lot of points. This is one section. So okay. You can see only the overbreak. Now I use the filter only the points in the surface the overbreak. This is my data. I can analyze to understand the cohesion and the friction angle. So in below and the up the surface, I can a lot of points, more than 1,000 points. That in this case, in the other, I think less than 30. So I hope this is better than the first example I put in the Excel. So I use the cohesion and the friction angle in my calibration mode, and I will check the results, and I compare for the failure surface. Now I change the cohesion and the friction angle. This is the model calibration. Check. This is very better than other. In yellow to red, the failure surface, my example, and the black line where the failure occur. Well, now I will close. I would like to a new opportunity here. So how the 3D block model can be made with integration. Franz explained about the block models. This is one opportunity. They integrate the data leapfrog and map3D into the Gen4D. Now, in leapfrog, I get the rock mass and the lithology. Map3D, I can get sigma 1, sigma 3, safe factor, the tube. I can put in the same data the empirical, example, N-line, hydraulical radius. And in Gen4D, I check always the database. One example, this is my mine, this is my plane mine, this is mining, this is points where occur the instability. I can generate the voyage, the instability, and in here, finally, I can see the influence the mine in my ramp and the other developments. So in the blue, the safe factor ubicus plane more than 1.5, and in the red, orange, less than 1.5. It's very good to understand when you put the ramp and the influence the mine in your primary development. Well, thank you very much. Sorry for my English. I need to learn more. Thanks, guys.
Thanks very much for presenting to us, Gustavo. That's really good. Have you got any questions?
Okay.
Thanks, Kim.
Thank you.
Thank you, Gustavo. Good job on getting up and presenting next year. Really appreciate it.
All right, last but not least, people still awake? All right, fortunately this is a bit of a lighter presentation and yeah, a good one to finish with, hopefully. Shouldn't be too long. We won't be getting into the chemistry, don't worry, because people are already checking out of here. Yeah, it's just a bit more of a safety awareness about, and pretty operational and practical to do with sort of the life cycle of resin cartridges and sort of some recommended handling and storage. What happens from the factory all the way through to sort of when you install it underground. For those of you that don't know, J-Lock resin, it's a polyester resin cartridge, widely used polyester resin, fiberglass plastics. The capsules are made up of two components, so your mastic, which is the blue colour there, but can be any colour depending on the speed, and the catalyst, which then get mixed together in the hull. The styrene note there is one that just to take note of there, because that is classified as a hazardous substance. Shelf life here, that's sort of what a data sheet will say. This presentation, I should also add, is relevant to pretty much all suppliers here. Yeah, shelf life is typically stated on a data sheet. Your different colour codes, all colour coded. Yeah, polyester resin over time naturally thickens and becomes more viscous, and the firmness of the capsule decreases. Age doesn't affect the strength development or performance, but people often complain that the resin's gone off or it's hard to use because of those factors there. So this presentation is a little bit about making sure that we keep it easy for the guys to use underground, and a little bit there on the safety. Like I just mentioned, polyester resin is pretty widely used, it's controlled. In the factory over in Sydney, the monitoring of styrene and environmental factors is closely done. And yeah, you can walk into the resin and everyone's probably smelt that smell. Pretty easy to smell, at less than 0.1 part per million. And styrene, yeah, it's denser than air, so it can collect below knee level in a container. And if people have been into the resin containers, there's a few photos coming up, and sort of just something that we just wanted to talk about just to make sure that people are aware of. But as you can see there, typically forklift operator is yeah, pretty low risk. So number 2 there is where the resin is made, over in Sydney, the J-Lock and Rock Bolt factory. Life cycle here is sort of what we want to talk about. So all the manufacturers are pretty much in control of the manufacturing, the coolage, the transportation to a warehouse, and then in this case, and the examples that I've got, cooling here in Perth. One example there of some data logging that we've done of that life cycle. So one up the top there in the corner, you can see the, where's the mouse? So yeah, you can see the manufacturing there, and it cools down, and the days that goes past that. So then transportation, cooling in the fridge there, that one was shipped out pretty quickly. Transportation across the Nullarbor, and then 4, it was stocked in the fridge in Perth, gets down to a nice stable cold temperature. At this point here, it's out of the manufacturer's control, and this is probably a takeaway point for anyone on site, is just to order to think what happens at that point afterwards. Nothing really mind-blowing here, other than the fact that you can see that day 27 it leaves there, and day 36 it goes into storage. Heat fluctuations affecting the resin properties. Can we reduce this time? How can site guys be aware of them with your logistics people, and you guys as engineers might not necessarily think about these factors, and to talk to your supply chain of how they can manage this. Obviously the winter, not really an issue. Here's an example from a summer one, and you can see there in those periods in the Sprinter truck coming across the Nullarbor at number 3, resin gets to 30 degrees. But they go on a site, peaks up over 40 degrees, and it takes quite a few days again for them to get it into storage. And then you look at the storage temperature there, underground, 32 degrees. And then we get to that point, and the guy there at day 60, 64, 65 goes and complains, oh, the resin's not working very well. And you blame the manufacturer. And then people go, oh, so what are the factors that can sort of control that? So you can then start to step through, and you go through, you come to site, and you look at what the storage on site's like. Pretty normal side opening container there, and the point I was making about styrene and safety. There's not a lot of room in that container there, as you can see. Site safety there, also, yeah, rollers on the floor, stock management. How do you guys manage that on site? And we start to try and work through this process with the individual customers of how do you manage it. So typically these are pretty good, and most of the suppliers have these roller doors with in and out, so you load the fresh stuff in one side and you take from the other side. Good stock management. We can step through it, look at the shelf life, what the data sheet says, and like I said, the strength isn't affected. If the product's stored pretty well, I've known of examples where resin at 18 months old has been used quite successfully, but the storage has been in pretty good condition. So it's worth just having a conversation there on your sites and with your suppliers about how you store that. And yeah, there's a picture of the Perth fridge with over 160 pallet capacity there. You don't really want to be letting it go off. And so when you have those issues of, oh, the resin isn't done very well, or the resin isn't performing, the guys back in the lab can compare the retained sample that's kept from that same batch, and you can compare it to the site ones, and then that quite quickly says, no, there was nothing wrong with the resin when it was made, something's happened to it along that process. So it's a pretty informed and well constructed manufacturing plant, and it can be traced all the way through that life cycle. You just have to take the information that's on the box, and those batch numbers can be traced all the way back. And the guys over there in Sydney do an awesome job with that research and development. So there's a lot of factors there on the technical side and the installation that not gone into, but if you need to talk to any of the technical departments. So yeah, that's sort of just a short takeaway, just to consider the safety implications of how you're storing your resin on site, and to consider your site usage there. And yeah, pretty quick one there. Just wanted to share some basics as summer's soon coming. And yeah. Lastly, any questions? And thank you again to Robin's team.
Very simple and very important. Have you do any test to see how much effect the strength of the resin after you have all this huge report?
Yep, we've got projects underway and there is data available.
Just a comment on this storage of these products. I'm going back to history, what I was talking earlier today. You might remember that some of the photos actually they were showing resin guarded boards. The problem at the time was exactly what you're saying now. So they store these products just outside sometimes under very high heat, and then they go off and they don't even know when these are bought.
Yeah. Well, exactly, and that storage and the implications of that storage is pretty important. There was a truck being loaded in summer last year, and they went outside with the temperature monitor, and the truck had been outside for 3 hours, and the temperature inside the top layer of that pallet was over 64 degrees already. Like the packaging there just acts like a greenhouse. So it's just about just making sure that the poor guy down there at the end of the cycle, over 1,000 meters underground, isn't suffering because people aren't looking after him further up the chain. So it's not really a major technically presentation, just sort of wanted to share that. And
Thanks, Anthony.
I think, yeah, the usual practice of going down for a beverage over the Melbourne down over the road. Brendan's always leading that charge, so.
Was that the last capsule that you showed for the...
Exactly.
All right, well, thanks everyone for attending today. Thanks to everyone for presenting as well. It's a very short day for now presenters, so thanks again. And we've still got spaces in Calgary if anyone's able and willing. They've got something interesting to present there. Our next meeting's in November. If anyone has suggestions for topics, you're welcome to share them, and we'll think about that. And yeah, just remember to maintain your distance from people in the lifts. Going down, it's probably going to take us about half an hour to get out of here, 2 at a time. So,
yeah, and I suppose the last
chatting on the way.
takeaway there for Rob is the committee worked hard for this, and we welcome your feedback on topics, how to improve and develop these sessions. It's great to see so many people here today, and hopefully Kalgoorlie on the 26th. Some people can attend, people on your sites, and the presentations today, there were some really high caliber presentations. Thank you to the Anglo guys. They don't all have to be like that. A few photos. This is a safe space. Get the guys up presenting just a few pictures. Doesn't have to be anything too crazy.
Great, thanks everyone.